It's a great honor for me to give a talk in front of this nice audience. I heard a lot about this center, and yeah, I hope that you can enjoy this talk. Today, I'm going to talk about my recent work on personalizing machine learning models for speech enhancement. And it has a lot of interesting complications behind. So it's a good problem for me to work on, although it's kind of challenging. So let me just share my problems with you so that interested people can work on this big problem, because it's like really difficult. And these are the students who worked on this problem, three of them. So just to give you an idea, let me move. Just to give you an idea, let me give you a brief introduction about speech enhancement in general, where we begin with this clean speech signal, and then by contaminating it with noise as well, so that we can simulate the mixed speech and noise, because that's what we can do. The reason why we need this kind of artificial mixing process is that we need the pair of input and the output when you train a machine learning model, and the input is noisy speech. For example, say we have like a lot of different clean speech signals from many different people with variations in there, and we can contaminate it with some non-speech noise like airplane or dog barking or whatever. And then the model is trained to learn this kind of inverse function of this mixing, which is G function here parameterized by W. And our goal is to train this model, the model parameter is W, and then estimate the clean speech. Of course, it's not going to be perfect, so that's why we have some pinkish noise in there. But if that's basically the traditional standard setup for speech enhancement using machine learning. So this is working, and like any other deep learning application area, it's working pretty well. Although there are some issues. For example, the deformation function f we came up with here, which is just simple addition of speech and noise, which is not always the case, because in this large room we have some reverberations involved in there and so on and so forth. But most of the time we can still simulate them. The bigger problem for me is that we have this big data and big models problem, because if you look at the deep learning advancements in the past couple of decades, it relied a lot on the big labeled data, the presence of the big labeled data. In this case, the pair of clean speech and the mixture audio, which is, again, not a big problem in our case, because we can always synthesize up this noisy speech compared to the other problems where people have to label the images into dog and cat, or sentences into different words. It's a much easier case for speech enhancement. But at the same time, we still need to learn a big model that generalizes really well to any different test time environments, because we don't really know what kind of noise is going to be added to what kind of speakers specific speech signals. So my biggest question here is that, do we really need this big model to solve this problem? Because the big models are problematic in many different senses. So let me give you a comparison between this generalist versus specialist. Well, usually if you're simple-minded, it's not that simple, but if you have some GPU resources and the data, then you can train a universally working speech enhancement system, combination of RNN and CNN and or whatever, funky neural network architecture, including transformers and so on. And then, you wish that this extended to many different test time environments. For example, user A, who is bringing around a dog, and you want to remove the dog barking sound, and the result has to be from the system. The result must be like a cleaned up speech of user A, and there's another user who's like using some drones a lot, and drones propeller sound is going to be noisy. And at the same time, I have a friend called David who's with some lots of birds. So if I'm on the Zoom call with him, there are some bird sounds, and sometimes I want to reduce them. But they're like very specific kinds of test environments, and this system has to deal with that. My suggestion is that, what if we can personalize this model into like this particular test time environment, and then let the model work only on that problem instead of this big problem. why do we want to do this instead of working on this big problem? Because everybody loves a big model, and the issue there is that though of course, first of all, we want to improve the performance. So let me give you an example here. So there's a mixer audio with speech and bird singing.
Are you looking for employment?
And if you choose the right specialist, which is specialized for bird singing noise reduction, you can do something like this.
Are you looking for employment?
But if you choose the wrong specialist,
are you looking for employment?
Here are the bird noise, right? So my point is that, yeah, I mean, if we can use the specialist, then we can expect that it works really well on that particular problem. But if you fail to choose that one, then it's not gonna work, right? So it's there are some other issues about the big models, by the way. If you just blindly collect a big amount of data from a lot of different users or speakers, what could happen is that although it's easier, I mean, it's time consuming and maybe expensive, but you can actually build a big data by just simply collecting them, but it's going to miss some issues. For example, like a few years ago, this face recognition systems became a big issue in some in the research community because it turned out that if the researchers here, they kind of downloaded off-the-shelf state-of-the-art facial gender recognition systems, and it turned out that as for the white, lighter skin, the males, their accuracy, the system for their accuracy was at 99%, super great. But when it comes to darker skin, the female subjects, the accuracy drops to 65%. It's simply because the machine learning model wasn't biased. It was biased because of the data set, which didn't care about this kind of social issues. So my point is that if we can personalize a model once it's trained, and if we can somehow like adapt it to the particular user, then maybe we can reduce this bias down the road. So to summarize, if I compare the big generalist models and the smaller specialist models, performance-wise, the generalist models, if they are trained from the big data and if it's large enough, then it's going to be overall good. Of course, the specialists could be even better if it's targeting on the right test groups. As for the generalization, since the generalist models are larger and it's trained from the larger data set, of course, it can generalize better. It means that if you train a model that's specialized for the particular user, then it's not going to generalize to the other users, of course. But we might prefer the specialist because the big models are computationally not efficient. If you want to, for example, use the speech enhancement system on your handheld devices, like for 2-hour-long phone call, then it's going to drain the battery because it's too large. On the other hand, smaller models can be more affordable for some mobile devices. Data efficiency is going to be another issue because in order to cover all the possible test time variations, the big models is like really greedy about collecting a lot of data set. On the other hand, as for the specialists, you don't have to maybe worry too much about the size of the data set, at least, although it has some other implications behind. As for training, big models are actually easier to train. I mean, it's going to consume more electricity, and it's going to take up more time because you need to wait for like maybe 2 weeks to converge. But at the same time, for the specialists, because the models are smaller, it's solving a smaller problem, sub-problem, maybe it will converge faster. The only thing is that training algorithm itself is going to be a little bit more complicated because there are some data-related issues which I'm going to talk more about. Biggest problem with the specialist or the personalized models is that their privacy preservation issue could be pretty substantial, because when you want to personalize a machine learning model, it means that you need the data from that particular person, and that particular person is not going to cooperate. I'm not going to share my data with big tech companies so that they are personalizing their models for me. Even if it's going to be beneficial for me as a user, I am reluctant to share my my voice because my voice is precious, right? And eventually, though, if we can achieve this kind of a personalization, I believe that we can achieve better social fairness because I'm Korean, I am immigrant. My English is with a heavy Korean accent. And because of that, I cannot use Hey Siri or Alexa because they don't understand my English. So what if they can personalize their models for me so that they can understand my accented English? That could be better. Okay. So my argument here is that if we can somehow personalize the models, then it might be beneficial for many, many different reasons. But how do we actually specialize a model for a particular person? Because the particular person is not known ahead of time because we are talking about the test time environment. When we learned machine learning in school, we learned that the test time data set has to be set aside and we shouldn't touch it. We shouldn't assume that it's known, right? So we kind of have to know ahead of time what we're going to do with this test time user, which is kind of a tricky problem. And this adaptation, if it ever happens, it has to happen during the test time, not during the training time. So it's a tricky problem. A naive approach to personalized speech enhancement would be, for example, you could collect some noisy speech of the target test time user. Oh, I'm super interested in this test time user, Minje Kim, because he's interesting. So you collect the noisy speech from this guy, and because he lives in some home, he has some refrigerator running and washer machine and dishwasher and everything. He has a kid, so the kid is making some noise. So he has a particular kind of test time environment, and then you can train your model using this data set targeting on his clean speech, which is a myth because the system doesn't have access to my clean speech unless I am willing to share my clean speech. Because, for example, if these days, when I get the robocall from FBI, I don't say anything. I pick up the phone, it says FBI, but I pick up the phone and I wait until a real person starts to talk to me. Because when I say something, maybe what if they just collect my voice for maybe 2 minutes and then start to do things like this.
Korean, but New Sapiens makes me to speak Korean. He prepared this technology to meet North Korean leader Kim Jong. Look forward to our meeting. See you guys soon. 내 이름은 Donald Trump입니다. 나는 한국어를 배운 적이 없어요. 그러나
I'm pretty sure that he doesn't speak Korean, but because he speaks a lot, we can collect his voice and then pretend like he spoke in Korean, which is my favorite demo, by the way. So I'm not as famous as former U.S. president, but of course, I should be worried about my progress, right? So that's the main reason. I don't want to share my clean voice with the big tech company, but at the same time, there could be some technical issues. I'm an audio guy, so I'm pretty good at recording my clean voice, but there could be some normal people who believe that they are recording clean speech, but actually the room is not that clean. I mean, it's noiseless, but it could be too reverberant. So it's kind of useless in that regard. So asking the users to record maybe 5 minutes long clean speech, even if they are willing to do that, there could be some technical issues. They think it's clean, but it's actually not clean kind of situation. So I'm going to try to introduce some algorithms that me and my students have developed so far. And I'd like to group them into 2 different categories. First thing is a zero-shot PSE, where we don't require any clean speech from the test time user. We somehow, although we somehow want to adapt the model so that it can kind of handle that unknown test time speaker, which is tricky because it's kind of impossible job. But we could figure out some algorithms that doesn't require clean speech from the test time user. And I could say as a user, I might prefer this solution because it doesn't require me to record the clean speech, and it somehow does that for me. So it might be a little bit more privacy preserving, although it's not going to be perfect. But at the same time, we don't have to worry about labeling this clean speech or recording clean speech at all. So it's going to be technically easier from the user's perspective. But the challenge here is that how do we actually achieve this personalization without any recording of the test time user? It's kind of a tricky problem. Few-shot learning-based approach would be to, assume that there could be like a very short period of recording available by the user, maybe 5 seconds or 3 seconds, 10 seconds, which is kind of doable if they cooperate. And then we can kind of make the best of this, very short period of time, and then, somehow adapt the model based on that. So it does require clean speech. So it might be something that the user doesn't want to do, but maybe it could be okay if it's a small amount. But with this, small amount of clean speech, maybe we can achieve better performance compared to the zero-shot PSE. But at the same time, this clean speech thing is really annoying for the users to collect. So it's going to be downside of this approach. And maybe the system can overfit to this clean speech if you overuse this 5-second long audio. So we need to figure out how to prevent this overfitting, which leads us to this interesting self-supervised learning issue. So let me introduce this first algorithm, which I am really excited about. Christian? Yes.
Yeah, sorry. I guess before you were introducing the motivations for personalized models, and it seemed like most of the differences were in the background environment. But then here for fine tuning, you're collecting the free speech. Have you guys tried instead collecting the background noise?
I didn't distinguish. So I basically applied the term personalization here because it may sound like the model is adapting to the person, not the environment. But actually, this one is actually not adapting the model to the person, but to the noise level. But you can actually adapt it to the person, or you can adapt it to both the person and the environment at the same time. So I'm kind of using good case. So in this particular case, we came up with this categorization of the speech enhancement problem into like 4 subgroups. Very, very terribly noisy case and a quite good case and so on. So it's because if you think of this problem, speech enhancement problem, there are like a really harder cases, like where noise is like really, really bad. Then you don't want to use a model that's specially designed for some already clean speech, right? So in this way, we can maybe come up with 4 different specialists ahead of time and then try to select them during the test. That's kind of basically the idea. And this architecture itself is not new. It's something called the mixture of local experts. But we call it sparse mixture of local experts because compared to the traditional version, this one, our proposed model actually select the only expert that's relevant to test and user, so that we can reduce the runtime complexity during the test time. So let me show you what's really happening. So during the test time, we have this noisy speech coming into the system, and then we are gonna basically feed that to this little classifier, which we call gating network. And this gating network, of course, has to be trained somehow so that it can, in this particular case, it can recognize, oh, this noisy speech is like a very terribly noisy case. So then, if that's the case, it says that, oh, I'm going to use this particular specialist because that particular specialist is specialized for that kind of noisy case. And then once that selection is done, during the inference, the actual enhancement is done only by using this selected best specialist, while the other specialists are not participating at all during this inference. In that way, we can kind of substantially reduce the inference time complexity because we are using only a very small model for this problem. So once this is pre-trained models are like in place and working, we can actually fine-tune this entire system so that, for example, this gating network can make some mistake, right? It is terribly noisy case, but it thinks that it's not that bad. Then it will choose some like a second best option. Then this kind of mistakes has to be kind of taken into account during training, and then fine-tuning can help out this part. If I show you the results, this green graph is the model that's not considering any of this modularization or model selection. And then if you see this blue graph, that's the case where Oracle case when the gating network makes the perfect decision. Okay, so then this orange case is the results from the actual model that's with some misclassification, right? So that's why the orange case is kind of somewhere in the middle between the baseline and the oracle. But what's really interesting to me is that this purple line, which is the fine-tuned result, which is surpassing the performance, the oracle result. It's because they kind of communicate each other. Oh, your classifier, you're making some mistakes. I'm gonna do better for you. And the classifier, of course, knows that the specialists are not that special, so it's gonna make some decision based on that. So why is it important? Because if you see the numbers here, for example, I can see that this guy over here is using a very much smaller neural network architecture, 2-layer, the 512, and it's achieving the best performance of the system that doesn't do any specialization. So we can actually expect that model compression is possible, or maybe improve the performance if the model size is the same. So there's no reason not to do this if this is the case. Another case would be actually to personalize the model to the person. And it's really kind of tricky because in this room we have like dozens of people. Do we really need like a per person model? Because there could be some people who share some similar speech characteristics, right? So then it's a we could partition this problem based on some kind of unsupervised clustering, right? So how do we cluster speakers into different clusters? I think this audience knows a lot about this. We can, for example, learn some speaker embedding ahead of time from the noisy speech, and then group them in the embedding space. We did it assuming that there could be 2 speaker groups, and it turned out that the grouping is kind of matching the gender of the speakers. So we figured that it's working. Okay, then how about 10 speakers? Now we have no idea what kind of guidelines the clustering algorithm was using, but maybe it's based on some clustering mechanism. And I can see that there are some nice clusters here. Okay, so in this way, what we can do now is that as for the noisy speech, we actually, when we trained this, when we learned this embedding space, we use the Siamese network to learn the embeddings and then compare them in the embedding space to figure out how similar they are. So we use the Siamese network's encoder part as the part of our classifier that we used earlier. So this part actually does this embedding that we are seeing over there. But this embedding is now fed to the softmax layer as a classifier, and it is making decision instead of noise levels. Now we are classifying this noisy speech into the speaker groups based on our previous clustering algorithm, and it does the same thing. So overall, this one works as good as the previous one. The drawback, though, is that we still need to carry around these k different specialists, hoping that one of them is going to be always used, right? So the model memory size is still large, so the spatial complexity cannot be reduced in this case. And the adaptation is kind of limited because we need to come up with a clever idea how to subdivide the entire problem. In this case, it worked, but there can be some issues if it's too predefined. So this is the result from the speaker specific models. And as you can see here, these lines are all the personalized models. And this black line is the result from the baseline model that's not personalized. So with the personalization, we can improve the performance by a lot. But what's really interesting to me is that if we increase the speaker groups from maybe 2 to 10, we can see some gradual improvement as well, although it's not that it saturates at some point. So we don't want to come up with 100 different groups because it's not going to be that useful. So this K number is, the hyperparameter that you need to choose. And then at the same time, if you do fine tuning, if you compare the thicker lines and the thinner lines are always better. It's because we did some fine tuning of the entire system and that lifts up the performance in all cases. So if you see the complexity analysis, you will see that this one over here, the smallest personalized model, and the this guy over here in the baseline, they are performance-wise the same, but if you look at the model size, actually it's a 95% reduction, significant reduction in terms of performance. Yes, Chris.
Sorry, on the x-axis, that's number of
parameters
per specialist or total?
For the specialist model, they are parameters. So the baseline is just, you know, it's not.
So if there's 10 specialists, 64
times 10.
Okay.
But for the inference, we only use one of them.
Okay,
So that's why
it's not dynamic. Okay.
So it can achieve some model compression without losing the performance, actually. So that's the case when we don't need any maybe reference signal, clean speech signal from the test time user. We only needed the noisy speech that's the input to the system, which we are going to use anyway. So that can be seen as a zero-shot learning case. As for this one, self-supervised learning can help out the case and then improve the performances. Where, for example, I know like lots of you are already familiar with this concept, but just to briefly summarize. In computer vision and NLP, for example, self-supervised learning has been really popular because it's a way to reuse some data set that's not labeled. So in our case, if we do have like a 5-second long clean speech audio of that particular user, what are we going to do with that? Because if you just train the model using only that part of the data, then it's going to overfit to that part, right? So we need some kind of pre-training mechanism that's robust enough. In our case, this is going to be noisy speech that we can collect. Like it might be difficult for the system to ask the users to record their clean speech, but maybe it's going to be easier for the system to record the noisy speech because the users are, they don't have to worry about the quality, right? So self-supervised feature learning can come into play to, maximize the utility of the noisy speech signal of that particular user, as in computer vision algorithms, such as this case, like, this particular algorithm assumes that there's a center text over here, and there are like different parts of the image, and the network has to figure out if it did these two pairs, then this is the left ear of the cat because it's a cat. So in order to make this kind of inference, like inferring where this other pet is from, the network has to know that it's a cat or an animal, right? So it's kind of way to let the model know the what's in there without any labeling that it's a cat. So things like that is possible. And in NLP, for example, say in Bloomington, we have a new chicken place on the third street. So I would say if the model has to estimate this marked word, then what's going to be the next word? Restaurant, chicken place, chicken wing, kind of there will be kind of the more popular choices, right? So in this way, although the system doesn't need any, the data set is not labeled, we can still learn something about the context of the sentence. So we're going to do something similar in this speech enhancement domain, where we will use some unlabeled or noisy speech. So let me briefly talk about this, the nature of the noisy speech signal that I'm talking about. This big data set G is the anonymous clean utterances. They are abundant, and you can just download it from the internet these days, LibreSpeech, for example, and they are good. You can train a big model out of this big data. Good. If you can afford it, go ahead and do that. But sometimes it's hard to personalize because you need to kind of match this one of them to your test time user, which is difficult. I wish I had this data set, which is the test time users clean utterances. And test time user is a weird person with a weird facial expression. So I want to kind of capture the peculiarity of that test time user by collecting the data from that test time user, but we know that it's kind of impossible. So as a alternative solution, I'm suggesting that we could use this S-tilde data set, which is from the test time user, but they're not clean. Some kind of random recording of that person collected everywhere. So it can be actually clean enough sometimes, but most of the time it's not going to be clean enough because of this noise added to there. So they're more available. They're not clean enough. But since we never know what the real clean speech is from the test time user, maybe we can still use this somehow. And since it's not labeled, it falls in the category of self-supervised learning. And let's see our first step towards this self-supervised learning, which we call pseudo-SP, pseudo-speech enhancement, because we begin with these unlabeled noisy occurrences that are already noisy, and we consider them as if they are clean. It means that, for example, we can add some additional training noise to that, meaning that the input is doubly noisy now, and then the target is the noisy speech. So since the target is not clean enough, it's not the real speech enhancement problem because the result is going to be still noisy. But we can think that it's a kind of similar process compared to the original speech enhancement setup where the target is clean. So that's why we call it pseudo speech enhancement. Once this is done, we could fine-tune this model using the small amount of clean speech that we can acquire from the test time user. So that's why this left part can play as a pre-training mechanism or self-supervised learning. So to visualize the process here, you could see that the original clean speech of the test time user is this, but it's always contaminated by this one. So the system has only access to this noisy version of the clean speech. Then it will doubly contaminate this by adding another noise source deliberately. And then now it has this final doubly mixed noisy speech. And the goal is, of course, to recover this guy because it doesn't know the ground truth. So target is already noisy. So noisy target training is another name of this process. So that doesn't work, by the way, because it's, of course it doesn't work. So one remedy to this framework is to actually purify this already noisy signal, which is a interesting concept, at least from my perspective. So just to summarize, we can assume that this desired set and the available set are actually pretty similar if the noisy speech is already clean enough, right? Do you agree with this statement, right? For some reason, the user is walking around in the quiet environment. There's no yellow noisy sources added to this user, but it never happens, of course. So what we are going to do is it's a kind of an opposite concept of data augmentation, which kind of blows up the number of data examples. So it's data purification, where we're going to examine this noisy speech, which we conveniently marked the noise and the speech sources differently, and then see if there are any frames that are clean enough by running some SNR predictor, which we train. So it's another neural network that predicts the level of noisiness from this unseen test signal. Of course, it's not going to be perfect, but as you can see here, compared to the ground truth SNR level, this purple line is pretty similar to the ground truth. It means that we could rely on this, non-intrusive switch quality estimator to find out which frames are more useful. Because here, if you look at these frames, they are kind of not useful because the noise is much louder than the speech, right? So if you kind of somehow reduce the contribution of these two noisy areas from this pseudo speech enhancement process, what we can see is that we can assume that maybe these two could be very similar to each other because we kind of wipe out the two noisy frames. And the results are like this. As you can see here, the black boxes are the baseline models, and the blue boxes are pseudo speech enhancement models, and it's kind of reducing the performance. It doesn't do any good, but actually by doing this data purification, we can refine the quality of this unlabeled data set by doing some kind of auto labeling, I would say, if you're familiar with the classification, then we can achieve the performance. What's interesting here is that if you look at this third column, the data purification doesn't improve the performance too much because the model is already too large and it can, do some substantial speech enhancement already. So this kind of thing, except for the learning, fine-tuning, it doesn't really matter. But when it comes to the small model, the model, even if the model is exposed to the large data set and everything, it has only limited capacity to generalize to this particular test time environment. That's when we can see a bigger improvement if we personalize the model. So that's kind of the idea. And we were kind of into this self-supervised learning for PSE, and we expanded this idea into something more similar to this SimClear work, where we have kind of positive pairs and negative pairs and contrastive learning and everything. Where let me briefly talk about it. So we still begin with this, already noisy speech, and now we doubly contaminate this guy by using two different noise sources. It means that now we begin with mixture signals that are different from each other, and after the pseudo speech enhancement, the results has to be similar to each other, because they stemmed out of this same noisy speech, right? But at the same time, there can be some negative pairs where we begin with some noise source, and then we add some noisy speech signals that are different from each other. But since they are contaminated by the same noise source, the mixtures are kind of similar to each other. So if the speech enhancement was done properly, then the result should be less similar than the input. So that's why we have the negative pair, which actually minimizes the agreement. It's kind of a nice variation just to follow up the computer vision folks, because they are doing a lot of research here. So that's kind of the idea. And just to give you the overview of this fine-tuning related self-supervised learning and future learning, this baseline approach can pre-train the model using in a regular data set, libre speech plus whatever training noise. It doesn't assume anything about the speaker. So you just train the model. And of course, it could generalize well if the model is large, but if it's not, then it's not going to generalize well. So you could fine-tune the model using the speaker-specific data set, maybe 5-second audio of the test time user plus some other noise. That's the standard recipe, I would say. But if you involve self-supervised learning, we can replace this speaker-agnostic clean speech with the speaker-specific speech, although it's noisy. So what's the benefit of this? Because this is clean speech, and this is not clean speech. We still need to do some pseudo speech enhancement. The thing is that even if this self-supervised learning-based approach uses noisy speech, that noisy speech is containing something about the target speaker, right? So maybe doing self-supervised learning in this way could further improve the performance compared to the earlier approach where it just relies on the big data set. Fine-tuning part is the same. I'm not going to delve too much into these bars because they're kind of difficult to read, but we tried a bunch of different self-supervised learning approaches, and we can see that the tiny models, small models, are really benefiting from benefiting from the self-supervised learning and the followed by future learning compared to the baseline, which was trained from the big data. So the gap is actually pretty substantial. It's more than 1 dB. It's all over difference. And another thing is, if you look at the bars in the same group, they are from the different amount of clean speech signal that we acquired from the target user. And we can see that if the self-supervised learning part was working really well, then the reliance to the enrollment signal, the clean speech signal, is kind of lesser. It means that if the system can learn something from this noisy speech, then we don't have to require too much clean speech from the test time user. That's what we wanted to show here. This is our latest work, actually, that uses this self-supervised learning and the data augmentation and everything. But this time we were curious about the potential of the neural speech synthesis system. So instead of trying to do self-supervised learning, we just tested out this potential of the neural speech synthesis, which basically can generate infinite amount of clean speech signal out of 3-second long audio. I don't know if you have heard of these, like the very recent one I'm not going to play the sound, but you can check out over there. It's Google's latest speech synthesis system, which works great. Like it can synthesize infinitely long speech signal out of only 3 second long enormous signal, which is amazing. Of course, the thing is though, I don't have access to their system because they didn't, I don't know if they open sourced it yet, but anyway, but I could download their, examples from their websites, which is already good. So we could, we compared this to another open source system, which doesn't have to be this bad, but in our setup, your t-test system was kind of bad. It means that the personalization performance and the audio quality wasn't that great. Compared to the audio LM, the Google system that's, again, we don't have access to the model, but we just collected the authors' exemplary examples. They're really nice. If you see the numbers here, from the audio LM, the speech quality is better than the European test, and preservation of the personality, according to the speaker embedding comparison, it's much better. So we just deliberately chose these two systems because depending on which t-test system we use, the performance of the data augmentation is going to be different, and eventually the personalization performance is going to be different. So as you can see here, this one is the case where we fine-tune the model using the synthesized speech data set. So we assumed that 3 second long audio is available from that target speaker, and then we generate, Google generated, but 21 second long additional audio for that speaker, and then we can improve the performance like this amount. Although what's interesting is that the other t-test system is not doing much better than that, because if you listen to this, actually, based on my 3 second long audio fed to this your t-test system, the results sounds like just average male speaker voice because it's not personalizing well. So my point is that data augmentation is also possible using t-test system, and it can actually help the personalization of the system as well. Our final algorithm is using knowledge distillation for PSA. It's actually going back to the zero-shot learning case, where we assume that there is a very rigorous teacher who's with theory of facial expression. He's very adamant about his opinion. He's frozen his opinion. He never changes his opinion, but he's always correct because he's a professor. Now, our assumption is that this teacher model is big and it's learned from a lot of different data, so it works well. And there's a student model which is small, and it's efficient because it's student, but it can make some mistakes. The thing is, as a student model, it can never fix its own mistakes because students cannot fix their mistakes. It needs some help from the teachers. So what we can do is during the test time, for the test time adaptation, we're going to first feed the input to the teacher first, and then teacher is going to clean up the speech and then give the result to the student, and the student will do its own job, of course, and then compare the results. And of course, professors are always right? So, you're going to consider this other result from the teacher as the target, as if it's the target, although it's not clean, but you have to assume that it's always correct, right? So then you can compute the loss, and then from the loss, you can, do the fine tuning of your student model, hoping that your teacher is always right. If your teacher is always right, which is the assumption here, the loss from the teacher is always smaller than the loss from the student model. And if it works in this way, maybe the student model can do some inference on the fly, but say, you have some teacher model sitting up in the cloud, and then you send some signals to the teacher if the student wants some updates, because you don't want to meet your professor every day. Maybe once every week, you update your student model. And then next week, it becomes better. So that kind of thing is possible. And we have some results here where, let me show you this particular case. We have this student model that's not fine-tuned using this knowledge distillation, and the student model that's trained from some better teacher. We actually tested blue teacher and the yellow teacher because blue teacher is actually better than the yellow teacher. You want to learn from the better teacher. So as you can see here, the performance are very similar to each other, but the if you look at the number of multiplier accumulation, the amount of computation and the model size, it's like a lot of compression. It's like 66 times lower computational cost. So the conclusion here is that personalization is meaningful if it works, because it improves the performance and it can reduce the model complexity as well. And it can reduce the model's bias if there's any imbalance in the big data set. But it's kind of difficult to acquire the personal labeled data because private data is something that the user doesn't want to share with the third party. And maybe because of that, it can breach the privacy. So we need to be careful and clever about this. And the zero-shot learning methods are kind of useful because they don't require personal data. And but it's a little bit tricky because we don't have data. So there are some different ways we saw today that are kind of working to some degree. And future learning is actually kind of much better than zero-shot learning because we can use some small amount of data, but it's prone to overfitting. So we need to do some self-supervised learning to help out the case. I think personally this is the most useful case of using self-supervised learning for speech enhancement, because for speech enhancement, you usually don't have the lack of data issues because you can just synthesize the simulate the mixing environment. Yeah, so I'm done here. I had some other demos I just wanted to show you, but I think I'm done here. And let me stop here.
Yeah, you want. We have another like 7-8 minutes.
Oh yeah, I just wanted to go over what I do. Like for example, I care a lot about the. I don't like big models because I like smaller things. So I work a lot on the binarizing the machine learning inference so that it's more suitable for small devices. And we also work on like a neural network based coding algorithms so that we can do some compression of the signal. And we also work on some music creation and education, personalization. I talked about it. It's me singing the song, and I'm off tune. So let me actually show you this. It's a karaoke system. We call it a deep auto tuner, which takes the bad singing as the input and then fixes it into something better. I'm gonna play some better sing. Huh?
Can make your sound better music?
Yeah.
I'm curious. Hey,
mama gonna be alright. Dry those eyes. Hey, mama gonna be alright. Dry those eyes. Hey, mama gonna be alright. Dry those eyes. Hey, mama gonna be alright. Dry those eyes. Hey.
The first one was the ground, like the good singing, and the second one was the off-tune version, bad singing. After drinking a lot of beer.
Hey, mama gonna be alright. Dry those eyes.
Third one is the fixed version.
Hey, mama gonna be alright. Dry those.
Yeah, it's like that. I'm not gonna play my own thing because it's kind of awkward. These are my students. Some of them graduated, so I just wanted to brag about the diversity of my group because they're from everywhere. Yeah, and we are living in this place called Lodi. It looks pretty because we are in the new building, but I think this campus is very nice as well. Yeah, we are funded by this many places, and students are getting jobs in these companies. Yeah, that's it. Thank you.
thank you.
Makes sense.
So how much do you think the performance of the personalized we can go for? Like how much do you like?
It actually depends on, it relates to the question you asked in the beginning. So if you can specialize more and more and more by narrowly defining your problem, then the problem becomes easier to solve. So you can kind of achieve better performance. But actually it depends on the model size as well. So if you have a big model that's already working well for that particular case, then even if you try to personalize the big model, there's no point because the big model is already working well. I'm talking about like a smaller models that is trained from the big data, but it wasn't capable of learning from the big data because of the lack of model properties and everything. In that case, we can kind of shift gears and then, you know, point it to that particular problem, then we can see the problem.
But my second question would be like, how you disentangle that when I give you more data for the speaker, that you are not learning the speaker instead of learning the environment, you're just removing the environment itself. Like, what is the, you know, what's, because I have two dimensions here, the noise and the speaker.
Yeah.
Do you learn more about the speaker and the noise became just a trivial, or you're moving the noise and the speaker became trivial?
That's actually the criticism that I received from the industry people, because
oh, yeah, so that was like a journal paper, like I didn't review it, so that's
no, I haven't actually. It's like they say that yeah, they sound all good, but what if the user changes the scene and all of a sudden if it doesn't work? How fast can you adapt to the new environment? Because you know this thing is like really kind of tricky to handle, and you know if you point to that particular like area, then you know the model is going to be like kind of slow to adjust to that. So yeah, that's actually some kind of challenge that I haven't had a chance to talk, but we could actually at least slowly, you know, move to that direction. Maybe you know 1-2 seconds of delay and so on. So it could be possible. But you know, if you use the like a generalist model that's more not personalized yet, it's not the end of the world. Actually, it's still doing some business. It's not, you know, it's just that it's not good enough. So.
So how do you anticipate this would scale up if you had a different speaker as the background?
That's actually another question, and I'm trying to differentiate from Microsoft research activities. Recently, they had this challenge for the deep knowledge question challenge, where they actually have this bigger problem of separating out the pitch signals out of the mixture plus noise, and then they define personalization as a target speaker speech expression out of the mixture of the problem. So my focus is more about model adaptation for that person, not the model they can extract that person. So there's like a kind of conceptual difference, I would say. And to go back to your question, I don't think it's going to be that useful. I would say, for example, say you have a mixture of 10 speakers talking at the same time, and you have a mixture of 2 speakers at the same time. Then I'll like try 2 different models, and then use this one by detecting how many speakers are there. That could be kind of a metaphor of this thing in the context of speaker separation. But I think what you meant isn't really directly applicable to this.
Well, not necessarily in the sense of speaker separation, but in the sense of if one of the environments you're dealing with happens to have another speaker,
Yeah.
how much confusion do you think the model would have with the fact that the environment now has speech content versus sometimes having a bird?
For now, my models have been assuming that there is only one single speaker in the environment. So if there's another speaker, then it's going to be confused. That's kind of a typical behavior of the speech and model trained from single speaker. So to address that problem, actually, we need to train this again by having multiple speakers in there, and there's a place a really different problem. The model has to be retrained.
Just because I feel it relates to what Najim was asking you in the sense that is the model really learning something about this specific speaker, in which case it doesn't matter if the noise, if the environment happens to have another speaker,
Yeah.
or is it learning something about speech, in which case that it matters if the environment has another speaker.
Yeah. The added speaker can actually add another kind of variation to the theme, which the model has no idea about and maybe totally confused. Yes. Another failure mode.
So I had a question which was triggered by something that Matthew asked you. So we know that users are not very good at giving you some clean speech because most common people don't have a good idea what it means.
Yeah.
But it would be more reasonable to say to people to give you their background noise, to give you again, just start talking, but stop for 10 seconds, stop for 30 seconds. And then on the back end, you could take that noise, take some other clean speech, and then create a pair, or ultimately take that noise, do some clustering like you did with speakers, but instead have specialists with different kinds of environments and use that noise to figure out which specialist is best suited for this particular user. So in other words, first of all, have you tried it, or secondly, others have tried it, or what's good or bad about pursuing that approach?
It's very reasonable and convincing idea. And I pretended like I'm a speech guy for this crowd, but I'm actually a source separation guy. So to me, speech and noise are just two different forces. So if I can specialize in these speakers, then I can actually specialize in noises, because I am an audio guy. I don't discriminate speech from noise. They are equally important sources to me. So yes, to go back to your question, the same principle can be just used for a model to specialize in the noise sources. I just didn't try it because it's kind of obvious to me that it's going to work. But there can be like a different application or implications from the user's perspective, because I am worried about recording my voice, but I'm fine with recording my empty room because it has nothing in there. So yes, I totally agree with your direction, although I just didn't try that.
So what do you do for bubble noise? Because it's also type of noise, right?
This is a challenging crowd, yeah. Yeah. I give up Babylon as for Babylon. But I think, to me, I don't know if you would agree with me, but say there is like a dominant speaker with a very loud voice, and some SUM of softer voices as a sum, which will form the Babylon. I think the system sometimes recognizes actually based on the loudness, and then could be possible, but I should be kind of careful about this statement. Yeah.
About the noise. So do you have like specific types of noise or mixture of noises?
That's a very good question. When I mix up speech and noise, I always think that we assume that noise is like one source, but actually it can be a combination of multiple sources. So it depends on the sound designer who stored the feeding. And for example, there's like ocean sound, but actually the ocean sound is the tidal wave plus the speaker sound. So then it's a mixture of those. And I think what I assumed here is that any non-speech thing happening in the mixture is noise, and assume that there's only one speaker.
If I could ask, I think it was slide 11. We had different formats of this, like the generalization. So, would you know what would be the third formats of the independent Muslim children? Let's say you have like actually, what would be the variance of all the 9?
So your question is like, if the wrong specialist was chosen, what's the performance, right? So it depends on the how wrong it is, I think. So the fine tuning, I just imagine I don't have any like empirical data, but say you have speaker group A and speaker group B is somehow similar for some reason, and it's going to be a confusion for the gating network, right? So then what that means is that the confusion, if the confusion often happens, then maybe during the fine tuning, the two specialists are maybe trying to like more different from each other so that the confusion is less. That's why we could always see some improvement from fine tuning, but that's just my guess because I haven't done any analysis.
That was like where my question was, whether it really matters you so that you have some type of grouping the user. But if you maybe did it sort of randomly, would it still perform well?
Oh,
How important is the type of thing?
I actually have no intuition behind this group. If the number of groups is like more than 2, if it's 2, then it's better to 3, I know. So I think I don't want any intuition. I believe that the software was done for some reason, and then it's a program performance honestly. So that's what I did. But I didn't like look into like how this group sounds like.
I was thinking if you maybe did some type of different clustering and that wouldn't work as well, or be about the same.
Actually, there's another thing. When we started work on this, we wanted to tie up the clustering part as a part of fine tuning so that the network can figure out the best grouping strategy given K, which is best for the performance, which is kind of done by analysis of A and B, right? But we actually haven't like tried too much about it. But I think fine tuning is somehow like moving away from the original K-means crossing down in the embedding phase, because that might not be the best grouping for this particular problem.
Actually, it's a very expensive way to do it, but I can imagine using the specialist selection as your clustering criterion. You take your training speakers, and then you create some clusters, you do some enhancement. And then for each training speaker, you find out which cluster best enhances their speech, and you put them in that.
Yeah, it's like a grand plan, like a total learning based clustering and gating and everything. We actually tried it, but it actually doesn't work because the network prefers to have some pre-trained components that it can easily start from, and maybe fine tuning can improve on it. Yeah.
And we speak about the clustering, like how you separate the data to is fine. Yeah. So if your data is unbalanced, like you have, so what do you do? Like you look about the difference in the noise or the speaker, or if you don't have enough data in type of speaker, you choose a different type of clustering.
So in other words, if you had lots of males, very few females, then you did cluster.
Yeah, for example. So how you manage separate your data into.
So this particular algorithm isn't gonna be able to handle that bias, because I think I tried to mention that it's based on the predefined cluster reading structure, and it still relies on the training data. And if the training data is biased, then I have no way to improve it, right? But there can be other strategies like the data purification, for example, which relies purely on the newly recorded noise bits of that, new speaker with weird bits trait. Then we can actually do some self-supervised learning from that and then adapt to that. So I would say, if you're worried about bias, then I wouldn't use this, but use that. Yeah. I have a brochure of remedies and you can search from.
Yeah, I think, is there any more questions or one more question?
I don't know, but I think we should let if students have a question, we take one.
Well, there's dinner later about it.
Yes,
Student question. All right. Let's thanks again our speaker.
Thank you very much.
Thank you. That was very good.
Very good audience.